Okay, thank you very much for waiting for the computer technology to sort itself out. It's the third talk of the morning. I shall try and make a rapid sprint for coffee. I can already feel the caffeine levels dropping in the room. Okay, so we've had some very nice talks so far this morning, and I actually in some sense there's not much more to add, except that I thought I would try and talk about the underlying solutions of the partial differential equations that describe cosmic strings, because that's where the link between strings and more terrestrial, their terrestrial cousins, superfluid vortices and superconducting flux tubes, are most obvious. And that's also where there's the still remaining puzzle about the evolution of cosmic strings in the early universe, which Paul alluded to. So there's an outline which this particular latex style insists on producing. And here's a picture. I don't know whether we've seen this so far, but it's kind of a NASA publicity picture, and it sort of sets the context for what we're talking about. It doesn't actually represent very much, but it's supposed to give an impression of the fact that the universe has some age, and also that it expanded and something interesting happened right at the beginning, and that there's some evidence that we can gain, as Paul was talking about, from the cosmic microwave background, which was laid down about 400,000 years after the Big Bang itself. Here's for WMAP, scratch that out, put Planck. It's a satellite observing this stuff and hoping to gain evidence about what went on right in the first 10 to the minus 36 of a second. Now what might have happened is that a tangle of cosmic strings were formed, and in which case they would still be around. They would have been decaying away, and essentially everywhere in this diagram would be filled with string, but not at a very great density. There'd only be a few strings per horizon volume at any one particular time. Thank you. Okay, just to emphasize that the model that we have of what went on right at that initial singularity was is very clear, very simple. It's called inflation. That's a whole other seminar or conference, really. And as both Anna and Paul were emphasizing, inflation also can produce cosmological models with cosmic string in them. And it's also very strongly motivated by, from the particle physics. It's actually very, one side it's very conservative field theories, which also produce cosmic strings very well. But not only that, string and M theory is of course a theory of strings, and they also can appear in the early universe in cosmological models based on string theory. And the interest for cosmology is that these strings have gravitational fields and contribute to the perturbations. You can go and look for them in the cosmic microwave background. They also decay into high energy particles and or gravitational waves, and we can go and look for those. So, as I mentioned, we can go and look for them in the cosmic microwave background, and we have pretty good, as Paul was saying, factor 2 theoretical understanding of what that is, and the factor of 2 is not an uncertainty, it's an either-or. This particular uncertainty also impacts upon our calculations of density perturbations. That's the distribution of galaxies resulting from the gravitational perturbations of strings, the gravitational lensing, how common that should be, and in particular, we really don't know whether we should be looking for gravitational radiation or for cosmic rays when we're looking for strings. So really one, which means that we should be looking for both. And the problem is that if you take the underlying field theory and simulate it, and then plot the centers of the strings in, say, some volume, which would be, roughly speaking, the size of the observable universe at any time in the universe's evolution, you would get a picture that looks like that. Whereas if you idealize the strings, the flux tubes, by a relativistic one-dimensional object, you would get something like that. The difference is that all these lots of little loops. So there's uncertainty about how much string there is in the universe, and in particular, how many loops of string. Okay, so I'll get into a little bit more detail about cosmic strings, and just to emphasize, I'll be talking about cosmic strings from field theory. There are many other talks about the other kind of cosmic strings, the ones that result from string theory and perhaps constitute one of the only possible ways to get direct observational evidence of string theory. Okay, so just as in condensed matter system, one can classify the string-like solutions to your field equations, whatever they may be, in two kinds. One, gauge or local string, the other global string. In this one, it's associated with a gauge symmetry breaking, and the string is characterized by a circulating supercurrent supporting a tube of some kind of flux. In the laboratory, of course, it's magnetic flux. In the universe, it would be some kind of other flux associated with a different gauge symmetry. A global symmetry has no flux. It's just associated with some spontaneously broken global symmetry, and its nearest living relative in the laboratory is a superfluid vortex. So in the superfluid vortex, you sort of have a normal phase down the middle and a velocity circulation around it. In our kind of string, the global string, there isn't actually anything circulating. There's no momentum, and that's because it's a vacuum string. There aren't any particles involved. Okay, so just to sort of set the scene in a little bit, because we're going to have to make some approximation, because really we think that the universe is described very well at all energies, even perhaps up including the inflation scale, by quantum field theory. So in an ideal world, of course, you would go away and calculate with that. But really, we're talking about very complicated field configurations for which we don't really have very good quantum field theory tools. And because we're talking about very large occupation numbers and bosons, then the classical field theory is a very good approximation for us. In the case that this classical field theory makes a string-like soliton with low curvature, so low curvature meaning curvature, the curvature radius large compared with the width of the string, then we can approximate the dynamics of the field theory just by the dynamics of the string, and the action, the equations of motion, go under the name of Nabu-Goto. And even that is rather complicated, and then we would very often like to make some sort of phenomenological model. We can approximate the strings just by little segments of string flying about, and you make a statistical model, or we can even just reduce it, as Paul and Carlos have done very effectively, to just a couple of dynamical degrees of freedom, the density of the string and its root mean square velocity. Okay, let's get on to the field theory, and we can compare and contrast what we have with the relativistic model and condensed matter. Actually, relativistic makes it a little bit easier. So this is the action from which we start. It's just a theory of a complex scalar field. It has this kind of simple quartic potential, Mexican-Hat style, with a temperature-dependent, if we're talking about thermal equilibrium, temperature-dependent minimum, which appears below a certain critical temperature, and we say that the symmetry, the global symmetry, the phase symmetry of this of the theory is spontaneously broken. Field equations are very simple. Just this set of this nonlinear second-order differential equation, relativistic wave operator, is given by some nonlinear, is driven by some nonlinear potential. So it's got some interesting solutions, and those solutions are string-like solutions, or some of them are. They're the ones I'm interested in anyway. So if you take a static, cylindrically symmetric situation, write the field equations like this, with a radial function and angular function just with changing phase by 2 pi as you go around, you find a straight infinite string. It's a solution. It kind of looks like this. There's a roughly speaking right at the middle, the complex field vanishes, and around that, just by continuity of the field, there must be a where the field changes by 2 pi, at the center, there must be some energy density, and that's the string. This is supposed to be a tube of constant of density, and basically the energy density is confined to a tube. More or less everybody knew that, and I gave possibly one of the world's worst descriptions of what's going on. But the one thing I just like to point out is that with these equations, one has 2 different kinds of mode, which is whose dispersion relations are the following. One of which is massless or gapless. The other has a mass or a gap. In the particle physics jargon, that's the Higgs mode, and this is this is the Goldstone mode or modes. So one massive particle and one massless. And so the solutions to these field equation can include excitations around the minimum, radial excitations around the minimum, and angular excitations around the minimum. Okay, so this is probably looking very familiar. It's connected to the time-dependent Gross-Pitaevsky equation, which describes superfluids, and the connection is through trying to establish a non-zero number density of the in the background. So if there's this overall phase rotation of the complex scalar field, then you find that there is indeed a non-zero number density, and then you're talking about a condensed matter system. Providing that's slowly varying, you find that the equation takes this form, which is pretty much equivalent, is in fact equivalent to the time-dependent Gross-Pitaevsky equation, which has a very different dispersion relation. And so this is one that, although it's the kind of ultimately it's the same equation, there's very, very different physics near this in this particular state. So that means that there are similarities and difference between global strings and the superfluid vortices. They're both topological defects. They're both zeros in complex field. They both have concentrated energy density. They both couple strongly to the massless or gapless modes. But global strings, as I said before, are vacuum strings. There's no particles, and global strings move differently. They have a simple equation of motion, which is basically that the acceleration is proportional, the local acceleration is proportional to the curvature. But for superfluid vortices, it's much more complicated because of basically they're moving with the self-induced fluid flow, and there's also the Magnus force and so on. So although one can look at them and say, oh, they're global strings, or oh, they're superfluid vortices, that's one has to bear in mind that there are significant differences. If there's a gauge symmetry in the game, then a particle physicist would say, you've got the abelian Higgs model, whereas a condensed matter physicist would say it's that I can't spell. It's a relativistic Ginsburg-Landau model. So again, we have this complex scalar field, but now we have a vector field to go with it, and some slightly more complicated field equations to solve. And I've written them down in a particular gauge, the temporal gauge, which is convenient for numerical solution. And again, one has these string-like solutions. The difference here is that the tube of the singularity, the zero of the scalar field, is dressed by a current in the a current in the of the gauge symmetry, and the tube fills up with flux, magnetic or generalized magnetic. And the other thing that happens is that there's no longer a massless or gapless mode, the famous Anderson, Higgs, Kibble, Guralnik, Engler, Brout mechanism. Good. Hagen. Okay, and again, similarities and differences between the strings and the flux tubes. Basically, strings are in the early universe are very nice and clean, whereas a flux tube in a real superconductor is very much it suffers from, for example, pinning, so it doesn't actually move so much like this ideal system out there in the cosmos. Okay, yes, the string is indeed out there in the cosmos, so we have to be, the equations of motion that I wrote down have to be complicated a little, because the fields are in an expanding background, and in cosmology it's most convenient to write down the expanding background in the following form: that you introduce a metric, it has a scale factor in front, which depends on conformal time in this way of writing the coordinates. So in a universe dominated by relativistic degrees of freedom or radiation, this function is proportional to tau, conformal time, which is in turn proportional to the square root of physical time. In a universe dominated by a non-relativistic degrees of freedom, that goes as tau squared, or t to the 2/3. So the temporal gauge field equations become a bit more complicated. You see these factors of a scale factor appearing here and here, which is tricky because it's most convenient to solve the equations in these comoving coordinates, but in the comoving coordinates the physical width of the string shrinks, and so eventually it's going to fall inside your lattice. So the idea is to modify the field equation so that you reduce the power of A here, which is kind of where the problem is, and you also, in order to preserve Gauss's law, you put in another dependence on A inside the Maxwell equations. And so the true physics is S equals 1. If S is less than 1, the physical width of the string grows. Under numerical simulations, you can check what effect this has by varying S. Okay, just a little bit of advert for the numerical technology. You want to make as large possible simulations as you can, because you want to simulate as large a possible ratio between the radius of curvature of the string and its width. So you need massively parallel computing. So in order to make this easier, not have to write the code every time, we developed a very simple library for parallel computing of partial differential equations in a periodic box, and it works very well. We're just working on a second release of it, and the advantage here is that we're looking for scaling on much bigger systems. So we've tested it up to 32,000 processors, and this is for the particular system at hand, the abelian Higgs model. This is the way that the CPU time per site per time step. So that's basically that if you have perfect scaling, no hits from communication, that should be a straight line. And in fact, this is such a straightforward, simple problem that it's not surprising that we have a straight line here, that it scales almost perfectly. Actually, the difficult thing is getting the Fourier transforms to scale, and also the I/O to scale. Okay, so if you bung it on a computer, actually this is a rather small computer. This is only a 256 cubed. so that I could visualize it on my laptop. What you're seeing there is the isosurfaces of constant energy density in the abelian Higgs model shortly after the initial conditions were allowed to evolve. And the initial conditions were basically just a Gaussian random field for the scalar field, and then everything follows from there. There's damping in the system because the universe is expanding, and then once the strings have formed, then they disappear. And how they disappear is a very interesting tale, and that's what I'll be talking about the last part of the talk. Okay, so the way to quantify how the strings go away is to look at the total length of the string, and we can measure that by just looking at the number of plaquettes with a field 0 in them, and add them up, multiply by the lattice spacing, call that L. The total volume of the simulation is V, and then you can define a scale which is essentially the average distance between the strings, which is the square root of V over L. And what you find is that just by L over V, just on dimensional grounds, that has dimensions of 1 over length squared, and it goes as 1 over the conformal time squared. So this is actually co-moving length and conformal time. If you want to translate that into physical length and physical time, you'll get the same answer. So the average string distance is proportional to time. So here's two different simulations, and in fact these two different simulations were done with different initial conditions, and they were done with different values of this S parameter, showing that the initial conditions and that S parameter don't actually make very much difference to the evolution of the strings. Okay, so basically every time you do a simulation of a string, you find that the average string, the network characteristic scale, grows linearly with time. So basically that's the assumption, that there is that the psi grows with time, and that's very interesting because you can work out the energy density as a result of that. You find that it decreases as 1 over time squared. 1 over time squared, in line with the total energy density, which is also decreasing as 1 over time squared, which means that the amount of string relative to everything else remains a constant, and that constant is Newton's constant times the string mass per unit length mu. Now, given that we're interested in the particular physics that seems to be producing strings is associated with grand unification, which gives g mu of 10 to the minus 6. You can see that if there is string, there isn't very much of it, but it will produce density perturbations of order 10 to the minus 6. Okay, so there's a puzzle here, which is that, okay, so the curvature radius of the strings, which I've called psi, is one scale on the network, and the other is the width of the string. And psi, especially now, when it's billions of light years, whereas W is 10 to the minus 15 of a proton radius. So how is energy transferred from this scale to that scale? And that's the big puzzle in these simulations. And transferred it is. Where it goes is no mystery. It goes into propagating modes of the scalar and gauge field. Not a very good picture, but it's supposed to give you the impression that there are propagating fluctuations in the fields. Features of the energy loss mechanism. Well, it makes the string decrease, its energy is 1 over time squared, or 1 over psi squared, which means that the energy loss rate is 1 over time cubed. Remember, psi, the string distance, is proportional to time. So that means that the power per unit length is proportional to 1 over psi, or that it's, you can equally phrase it, it's independent of the string length. So a loop of string with length psi will radiate with a constant power, and its power is equal to the mass per unit length. So this is very strong, and much stronger for these kinds of in these simulations than gravitational radiation would be. And part of the clue seems to be, part of the answer seems to be that the strings actually are not smooth. They have small-scale structure. So you can work out what their fractional dimension is by measuring the distance you go in real space relative to the distance you go along the string in a simulation, and you can define the fractal dimension in this way. So S is distance along the string, R squared is mean distance in real space. And there's actually a prediction based just on scaling. This is in fact the only scaling fractal dimension which is allowed, and this index here is given in terms of the mean square velocity of the string and the expansion rate of the universe. So if you plot this fractal dimension against the distance along the string, you do indeed find a straight line, this power law, and it compares reasonably well with the prediction. We can go and look at the loops in the network. There aren't very many. This is the number per horizon volume, so that's volume T. T is time since the beginning of the simulation or the beginning of the universe. And the number of strings, number of loops of string per horizon volume is of order 1. These are different size categories. Okay, just to summarize the general features of string simulation, string networks in the abelian-Higgs model. So the long strings scale. So what that means is that they grow in their average separation grows in proportion to time. Their energy goes into radiation of the fields. Long strings are wiggly. They have a distribution of perturbations on them. There aren't very many loops. There's only approximately 1 per horizon volume. And the question, how does the large-scale oscillation make radiation of a very much higher frequency, seems to be answered by the presence of wiggles on the string, because they exist on all scales down to the scale of the string width. So it raises the question: is the Nambu-Goto approximation the correct one for field theory strings? Because the Nambu-Goto approximation says that the scale of the string width is not important, whereas the abelian-Higgs model simulation seem to be saying that it is. Okay, so I'll just summarize. So cosmological models based on field theories that we see occurring in particle physics have cosmic strings. Not all of them, but many of them do, which motivates thinking about them seriously. There are different kinds of string, global, local strings, and their relatives are superfluid vortices and superconductor flux tubes. They're formed in phase transitions in the early universe. I didn't have time to talk about that, but they can either be through the Kibble-Zurek mechanism or flux trapping. And the decay of this network, this tangle of strings that are formed by the phase transition, is self-similar. And somehow energy is transported from the curvature scale to the string width by a mechanism involving the small-scale structure on the string. So if that's true, then for all ratios of a curvature scale to string width, then particle production is the way to look for strings, and there are strong constraints from cosmic rays in that case. On the other hand, if something qualitatively different happens for very large psi relative to W, and nobody really knows exactly what very large might be here. If particle production then turns off, then we should be looking for gravitational radiation, and there are strong constraints there as well. Okay, thank you very much.
It seems to be a very close analogy, because there's the same problem with superfluid helium vortices, the problem of cascade of energy. And there is a consensus that reconnections are critical from that point of view. How does that feature here?
Yes, I think the consensus in the cosmic string community is that reconnections are essential in transferring the energy from the long string network into whatever into the short scale degrees of freedom. It's kind of in one case they're generating, the reconnectors are generating regions of high curvature. That's for the field theory. I think that's important. And in the case where you've got the line approximation, the Nambu-Goto approximation, again the reconnections are generating loops of string, which seems to be generated on a very, very wide range of scales, possibly the whole range of scales. So yes, reconnections are important as well, but there are differences because in superfluid vortices there are these long range forces between the vortices, which may or may not be important.
Yeah, I mean on similar lines, so the model is different for superfluids, but I mean it's also the picture very common of generating wiggles here by interacting Kelvin waves, so-called helical waves on vortex lines, which basically generated originally by reconnection. The break in the line will relax itself into propagating waves, but then these waves interact with each other and transfer energy to shorter and shorter scales until eventually they reach scales, they push closer to the core radius and strongly radiate. So that's I wonder, these wiggles mentioned in your talk a lot, and in previous talks too, but waves were not mentioned. I mean, I wonder if anybody looked into propagating and interacting waves. Not the radiation itself, but the waves on the helical waves on the strings.
Waves on strings, yes, people have looked into that. On the cosmic strings, it's rather different because the very small amplitude waves are very linear. There isn't.
If they're small amplitude.
Yeah. I think that there is. I mean, for example, waves aren't helical because there isn't a helical wave of one helicity and of the other is that both are solutions. But yes, I mean the short answer is the short caffeine deprived answer is yes, there is a lot of interest in the waves.
That's a turbulence picture where energy is transferred from larger scales to smaller scales. The difference with hydrodynamic turbulence that it's not eddies that break up into small eddies, but longer waves generate shorter waves via resonant interactions.
Thank you. Yes, I'm sure that we have a lot to learn from the community which has studied superfluid turbulence.
Okay, let's thank everyone from this morning session.